Hello, in this video I'm going to be talking about enzymes and also about redox reactions, which are when we oxidize or reduce something. So first of all, we need to understand what a catalyst is. A catalyst is something that is used to increase the rate of the reaction to make it happen faster. They are a substance that in the reaction doesn't actually break down or change in any way, so it can actually be used over and over and over again in that reaction. And in bio, we talk about enzymes because they're organic catalysts, which means that they are in living tissues. So we could talk about the enzymes that we use in the mitochondria, which is an organelle in the cell that breaks down sugar into energy, which we're going to be talking a lot about in this chapter. They're made up of proteins, which we're also going to talk about later in this course, what proteins are. So they're able to cause reactions to happen at body temperature instead of having to increase the temperature to make it happen faster. So the reason that we need them is because normally reactions happen really slow. Okay, it could take hours or days to happen. But unfortunately, in our body, we need them to happen a lot faster in order to survive. Okay, normally when we're doing chemical reactions, the way to make it go faster is to increase the temperature, or you can agitate it, or do a bunch of other things. But unfortunately, in our body, we can't change the temperature. Okay, it can destroy our proteins, it can damage our cells if we change the temperature. That's why having a fever when you're sick is usually not the greatest thing to have happen. So enzymes increase the rate of reaction, but you don't have to worry about changing the temperature at all. You can always just stay at a constant body temperature while we use enzymes. The reason why enzymes are important is because of something called activation energy. So normally in a reaction, in order to get it kind of started, it needs a little bit of a push to kind of get started. So it's kind of like rolling a rock down a hill. Imagine there's a giant boulder, the top of a hill. Okay, the boulder's stuck there, but if you can get the boulder kind of moving, it's going to just basically roll down the hill by itself. So that activation energy is the push that that rock needs in order to start rolling, and then once it rolls, it can kind of just go on its own. So we're trying to push the boulder down the hill. Energy is required to start any chemical reaction. So basically what an enzyme does is it lowers that activation energy. It doesn't need as much energy to get started, which means that it's going to happen faster because it doesn't take as long to build up that energy needed. So this is what a graph would look like in order to compare an enzyme reaction without an enzyme. So we can see that the activation energy with the enzyme is a lot lower than the activation without. So enzymes are also specific to substrates. So substrates are substances that we need to kind of bind with the enzyme for it to work. So whatever we're doing with the enzyme, if we're building something or if we're breaking something apart, that substrate would be that something that it's building or breaking apart. So whatever it's building or breaking apart can attach to the enzyme on what we call the activation site, which is the area of the enzyme that has a special shape where that substrate can kind of fit in nicely, kind of like a lock and a key. So the key has to go into the keyhole in order to actually open the door. So the active site of the lock and key mechanism would be the keyhole itself. And then the substrate would be like the key. So that's basically what I was just saying out loud. Okay, they have to fit together nicely, like a 3D shape of the enzyme, and they fit together like a lock and a key. So there's a whole bunch of different reactions that happen in our body. Okay, each reaction is catalyzed by a certain enzyme. So if we were going to look at the enzyme and its substrate, they usually have it fit together. This would be the active site. These two things fit together. Okay, if we're looking at other substances that you find in your body, this wouldn't fit with this enzyme. This wouldn't fit with this substrate. So they just have specific enzymes for each substrate because they have that specific 3D shape. Okay, just like if I have a key to my house, I can't go to my neighbor's house and open my neighbor's houses with my key because it has a different shape. And when we're naming an enzyme, we have a specific unique name that we give to it because it only acts on that one substance. So for example, later in this course, we're going to be talking about different types of sugar. Okay, there's a sugar called sucrose that we can find in certain types of food. And the enzyme that our body has in it that breaks it down is called sucrase. So normally the kind of general rule for enzymes is we usually use the start of the word for the substrate, and then we always end the word in ase if it's an enzyme. So if you see ASE at the end of a word, it's definitely an enzyme. When we're talking about enzymes, depending on the type of enzyme that we're looking at, how we turn these enzymes off so that we're not constantly building things or breaking stuff down. Sometimes we don't want to actually use them. So, competitive and non-competitive inhibition are ways that we can kind of temporarily turn the enzyme off so that it's not constantly using up all of our energy to do these processes. So, competitive is when we have a substance that will bond to the actual active site, blocking the substrate, the thing that is building or the thing that's being broken down by the enzyme, can actually bind to the active site. So it's called competitive because this inhibitor is competing with the substrate for the active site. The other type of enzyme inhibition that we have is called non-competitive. So this time the active site is still available for the substrate, but the non-competitive inhibitor will actually bond to a different area of the enzyme, which when it's bonded, it will actually change the shape of the actual active site. You can see that these are now kind of poking in. So now the substrate can actually fit. So it's not competing for the same place. It's still doing the same process where the substrate is still not able to fit, but it's just doing it in a different way. So we do have to know the difference between these two types of inhibition. Remember, this is so that we can turn the enzyme off temporarily so that we are not constantly using it and using up energy that we might not have. Now, enzymes are awesome and we love them, but they have some issues with them. So first of all, we have to know that enzymes are proteins, okay, which means that temperature and pH can affect them. So if we change the temperature or the pH, basically what happens is the enzyme will actually unfold. So remember we talked about the 3D shape is really important to the enzyme because the 3D shape then makes it so that the substrate can fit with it. So it would be like if I took the keyhole and I melted it down and it now became like this blob of metal, the key would probably not fit into that keyhole anymore. Okay, that's what denaturing is. And we have to make sure that we don't do this to our proteins, which are enzymes, because otherwise we can't use them. So just so we know, typically optimal temperature when we talk about a protein or an enzyme is usually when we're talking about our body around body temperature, which is 37 degrees Celsius. There also is the good pH range for a protein. So if this protein is found in the stomach and your stomach's pH is 2, this enzyme's optimal pH would be at 2. If it's found somewhere else in our body, which our pH in our other parts of our body is around 8, okay, 7 to 8, that would be the optimal pH. So if we change the pH of that enzyme, it could also go through that process of denaturing and basically unfold and unravel and then no longer has the same 3D shape. So another thing that I wanted to talk about today in this video is talking about reactions. So in reactions, when we have a compound that loses electrons, we call that oxidation. If we have a compound that is reduced, that means that it gains electrons. So I have a trick that I use, and you might have learned this if you've already taken chemistry. Leo the lion goes grr. Okay, so Leo is the lion's name, and it goes grr because it's a lion. So Leo stands for losing electrons, means that it's oxidation, and grr stands for gaining electrons, is reduction. Now, this doesn't necessarily make sense to us right now because maybe you have no chemistry background yet, but basically what you need to remember for bio is if we're breaking something apart, those electrons are going to be lost. So we broke bonds within the substance, and the electrons that were there to make those bonds and make sure that all of the valence shells had the correct number and this molecule is happy and content. Okay, if those electrons are then kind of separated, those electrons are sometimes going to leave those substances and kind of float around in the environment until it finds something that needs them. So if we break something apart, you lose electrons, which means that you're going through oxidation. So if you're oxidizing, you're breaking things apart. If you're reducing something, that means that you're building it. Okay, you're gaining electrons when you build something because you have to make sure that the electrons are the right number. Because otherwise, if the electrons are at the wrong number, that compound isn't going to stay together properly. Okay, the way that we form bonds is through sharing electrons or by making sure that they're equal amounts, that we have 8 or whatever element that we're talking about. So if we're building something, we have to steal electrons sometimes in order to build it properly, and that means that reduction is happening. So that's kind of what you need to remember for bio. If you need to kind of make sense of it, okay, that's kind of the most important part. If you already have done chemistry and you understand Leo the line goes gur, okay, you can use that trick as well. So hopefully this makes sense. If not, please feel free to ask me any questions, and I'll talk to you guys later.